Hello everyone and welcome to our talk on distributed planar reachability in nearly optimal time. So let me start by introducing the standard CONGEST model. This is a message passing model where the communication network is abstracted by an n-vertex graph of unweighted, undirected diameter d. The algorithm works in synchronous rounds, where in every round, every node can exchange log and bits of information with each of its neighbors. And let me mention that even though in this talk we are going to consider directed graphs, still the communication graph is bidirectional. The key complexity measure is the number of rounds required to solve the problem. And of course, the local computation comes for free. So in this sub-area of providing efficient global graph algorithms for planar graphs, our goal is to provide algorithms with round complexity that scales with the diameter, roughly with OD rounds or poly-D rounds. For many graph problems like minimum spanning tree, shortest path, etc., we do have a lower bound of d plus square root n many rounds for general graphs. However, if you look at the lower bound graph example by Dasserma, this lower bound graph is highly non-planar, which gives the hope that one can do much better. And indeed, in works by Ghaffari and Hoppler that introduced this line of works, they provided efficient algorithm that runs in nearly optimal time of roughly the diameter many rounds for minimum spanning tree, minimum cut. By now we have additional algorithms for DFS, approximate SSSP. Let me also mention that last year in a work with Jason, we provided a unified framework that I'm going to mention later on that is very useful for computing distance-related problems. For example, we can compute a 1 plus epsilon approximation of the weighted diameter of the graph in roughly poly-D many rounds. If you insist on solving the exact diameter, then the round complexity becomes linear by a new lower bound. Okay, but in this work, we are going to consider a new class of problems, reachability problems that haven't been addressed before in this setting. And we are going to have two main results that I'm going to mention here. The first result concerns the problem of the single source reachability. In this problem, given a directed graph of unweighted, undirected diameter d and a source node S, it is required to identify the set of all nodes that have an incoming path from S. So for example, in this figure, the set of all yellow nodes should output, yes, we have an incoming path from S. For this problem, we provide a nearly optimal algorithm that runs in OD many rounds, and this improves the implicit algorithm in our work with JSON that ran in D square many rounds. Our second key result concerns the perhaps most general reachability problem, where the goal is to identify the strongly connected components of the graph. That is, in the output format, it is required for every node to output an identifier so that all nodes in the same strongly connected component will output the same identifier. So in the picture, you can see that the set of all nodes in a given color correspond to a particular strongly connected component in the graph. For that problem, we also provided a D-round algorithm. And let me mention that previously we had no algorithm for detecting, no non-trivial algorithm for detecting the strongly connected components in the graph, not even for general graphs. So before I describe more on how we compute the single source reachability problem, let me mention few algorithmic tools from prior works that are going to be quite useful in our setting as well. So the first tool is that of balance cycle separator. Indeed, if we look at all algorithms, most algorithms for planar graphs, they are all based on these basic, very useful notions of a separator. A separator is a set of nodes in the graph whose removal breaks the graph into components such that each component is smaller by at least some constant factor than the original graph. In a seminal work by Lipton and Tarjan, they showed that any planar graph has a separator of 13 with a nice structure. The separator is made of two shortest paths plus one additional edge, ends forming a cycle. And we call it a balance cycle separator because if you look at the interior part inside the cycle and the exterior part, each of them has at most 2/3 n vertices. Okay, and the size of this separator is only order of d because it is made of two short espace plus one edge, so it has a size which is linear in the diameter of the graph. In a work with Mosen a few years ago, we presented a distributed algorithm for computing this balance cycle separator in roughly nearly optimal time of OD rounds with high probability. That algorithm worked only for bi-connected graphs, but since then we actually know how to remove this caveat, and this algorithm can be made general. So usually when we want to compute and use separators in some algorithmic context, it is required to compute the separator not once, but actually recursively, so that we will break the graph into smaller and smaller and smaller pieces and work in some divide and conquer manner. The problem is that if we just apply the distributed algorithms for a balance separator once, after we remove the separator, it is true that we got two connected components, maybe even more, that are smaller, but the diameter of each piece might be arbitrarily large. It might be even linear in n. And that means that once we continue with the recursion, the time complexity is going to scale not with the original diameter of the graph, but rather with a larger bound, maybe even linear. This is why with JSON, we provided a recursive scheme for applying this recursive balance cycle separator in a recursive manner, but in a very careful way that provides us two useful properties. The first one is that throughout the recursion, whenever we decompose the graph based on the cycle separator, the subgraphs are going to have a diameter that is bounded by roughly d, which is the diameter of the original graph. So it's bounded diameter. The second property is that if you look at all the subgraphs in the same recursion level, these subgraphs are almost edge disjoint. And that means that the distributed algorithm can work on all these subgraphs in parallel, simultaneously, without paying any overhead of congestion. Okay, and lastly, the leaf subgraphs in this recursion are going to be small. They are going to have roughly order of the many nodes. So one level, the first level of the recursion, just take the graph, it computes the cycle separator as you see here, and we get two subgraphs, the green one, which is the interior, and the external subgraph, which has now a hole, a face in it. But if we want to describe this procedure in a recursive manner, it is convenient to view the recursion tree, what we call the BDD tree. And this tree has a root node that corresponds to the graph G, and then it has two childs corresponding to the two components that you get after applying the cycle separator until you get to the leaf components. And because every node is defined by the computation of a balance separator, the depth of this tree is going to be logarithmic. And this bounded diameter decomposition is quite useful for solving many problems in a bottom-up manner. All the leaves are very small, so every node in a leaf subgraph can just collect its entire leaf subgraph, solve the problem on that leaf node, and continue propagating the solution up the tree. And we are going to see such examples. Okay. So far, I described a very ideal situation where you compute a cycle separator, and this is the picture that you get. But in truth, the situation might be more complicated. And the first complication is that, as we said in the balance cycle separator, it is made of two shortest paths plus one edge that might not be in G. For example, if the graph is a tree, you don't have a cycle at all, right? So in this cycle separator, at most one edge is not in G. And in case that you have such an edge, this is the red edge, it complicates things. An additional complication comes from the fact that in certain cases, when you compute a balance cycle separator, to provide all the nice properties of the bounded diameter decomposition, we cannot break the graph into two pieces, internal and external, but rather we have an internal piece and several external pieces, as we have here. So the BDD tree is not necessarily a binary tree. It might have even degree of D. Okay, but let's forget about these complications once I admitted that they exist and continue imagine throughout the talk that we actually live in a perfect world. Okay. So finally, before we proceed to the actual technical part, let me mention that usually, as I said, a key notion in algorithms in planar graphs is the separator. But for various technical reasons in this paper, we had to extend a bit this notion of a separator, and we defined the notion of extended separator set. So for a given subgraph G prime, for example, this guy, the extended separator set contains all the separator nodes of the subgraph, but in addition, it also contains the separator nodes of all its ancestor subgraphs. And since the depth of the BDD tree, of the recursive decomposition tree is log n, every subgraph has at most log n many ancestors, and the separator, the extended separator set that is denoted by SEP+, is still going to be bounded by the polylog n size. Okay. So really what I want to explain a bit now is about the single source reachability problem. And the key problem that we had to solve there is what we call the computation of reachability preservers. So I'll define the notion of reachability preserver. We'll see why it is hard to compute it efficiently, and we'll see some flavor of how to mitigate these challenges. Okay, so what is a reachability preserver? We are going to look at a subgraph, G prime. It's one of the subgraphs that I get throughout the recursive procedure, okay? And this, the preserver H of G prime is a graph. It's not a subgraph, but rather a graph that encodes all the reachability relations between all the nodes in the extended separator set of G prime. Okay, the vertex set of this preserver is going to be just the SEP+ node, and I'm going to put an edge between U and V in this graph if and only if there is a path from U to V. So this is a typo, it should be from U to V in this graph. For example, in this picture, we have a path from U to V, and therefore there's going to be an edge from U to V. So it's important to know that even though the graph G prime is a planar graph, the preserver might not be planar. It might even have d square many edges in a case where there is a directed path between every two nodes in the extended separator set. So the total number of bits in this preserver might be large. So here is our computational task. We are looking at this bounded diameter decomposition, this recursive decomposition of the graph based on balance cycle separator. And for each subgraph in this decomposition, for each subgraph G prime, our goal is to compute the preserver of this subgraph. That is, it is required for all the nodes in this subgraph to learn all the edges in the preserver. Okay. Once we have that, the reachability labels, which I haven't defined here, and the single source reachability are going to be computed locally at each node. So this is the only thing that we actually need to gather from the network in order for the nodes to determine if they are connected, they have a directed path from S or not. Okay, so this is the key computational task. Okay, so we are going to do it in a bottom-up manner. Okay, we are looking at the leaf level. At the leaf level, everything is easy because we have a collection of leaf nodes. They can just collect the entire leaf subgraph information and compute the preserver. But in every independent step of the recursion, we have the following scenario. We have this parent subgraph G prime that has two child subgraph, G prime out and G prime in, and we assume that we have already computed H of G in, the preserver of G in, and the preserver of G out. Okay, the nodes of these subgraphs, they know it. Our goal is now to compute the subgraph of G prime. Quite an easy observation is that this preserver can actually be computed once you know the preserver of the internal part and the external part, okay? And the reason is that if you look at any path between every two nodes in the extended separator set, this node and this node, this path is made of segments. Each of them is either fully contained in G in or in G out. So if I give you both subgraphs and you just compute reachability on that subgraph, you have the entire information that you need on the directed path in G prime itself, okay? So now what's the problem? Okay, all the nodes in G prime in, they know their preserver. All the nodes in G prime out, they also know their preservers. But now I want the nodes in G prime in to know about the preserver of G prime out. So we need to broadcast these edges. The problem is that if we just let the nodes broadcast the set of edges in a brute force manner, edge by edge, it might lead to a d-square round algorithm, because we said that this preserver that has roughly d many nodes might have d many edges. So we cannot just broadcast these edges of the preserver in a brute force manner. Instead, what we would like to do is to compress the information into fewer bits, into roughly d polylog n bits, such that when all the nodes get this compressed information, they will be able locally to recover all the d-square edges of the preserver. In general, it might not be possible to do that, but here, because of the certain properties that it encodes the reachability of the separator nodes, and we are living in planar graphs, as we are going to see, you can obtain this kind of compression. Okay, so let me pinpoint at the challenge a bit more in a more specific manner. We are looking at a vertex, this red vertex V, that is part of G prime out, and it knows the preserver for G prime out. It knows all its outgoing neighbors, but it might have order of d many outgoing neighbors. So we can't just let him send this number of neighbors to all of them, because we are going to have roughly d many nodes sending d many bits of information. That will be d square, and that's too much. Instead, I would like the node V to compress the set of outgoing neighbors in the preserver using just poly log n number of bits, plus additional d global bits that are going to be used by all the separator nodes in this graph, okay? But with the point of view of V, it only needs to send poly log n many bits to compress all its outgoing neighbors in these few bits. And this compression is made possible due to two structural claims. The first claim says that if we look at the nodes of the extended separator set in G prime, these nodes are not scattered arbitrarily in G prime, but rather they are quite nicely organized in order of log n many faces, okay? So the second property is that if I'm given two faces and I would like to encode the reachability information between the nodes lying on these two faces, I can do it very efficiently, and I can compress this information with number of bits that scales linearly in the number of nodes on the face, which is roughly d in our setting. Okay, so for the first structural claim, the fact that all the separator nodes lie on almost faces, this you can see on the figure, and because we avoid all the complications regarding these separator nodes, you get it here for free. But actually, if you consider the complications, we need to work a bit harder to show the first claim. But this one, let's assume that it holds. And I would like to focus on the second part, how to exactly compress the reachability information between nodes lying on two faces. Okay. Once we have these two properties, we will be able to compute the reachability, to compress the reachability information in just d many bits. Okay, so here's the key lemma. We are going to look at two faces, okay? And because these are just two faces, without loss of generality, I can assume that one is inside the other. So I have f external and f internal, the internal and the external face. And I have some node V lying on the external face. Our goal is to compress all the nodes on the external face that have an incoming path to V using just polylog n bits plus order of roughly d many global bits. So here is what we are going to do. We are going to look at all the nodes on the internal face. And I'm going to partition them into two parts. The green parts, these are the positive nodes, nodes that have at least one node on the external face to which they have an incoming path. Maybe they don't have an incoming path to V, but they have at least one node on the external face to which they have a path. And the negative nodes, the no nodes, the nodes that have no incoming path to any of the nodes on the external face. Those are the nodes that we don't really care about. So now that all the nodes in P, they can just broadcast it to all the nodes in the network. We don't have the budget for every node in P to tell us which are their outgoing neighbors on the internal face, but they can at least send us a bit and say, hey, I have at least one node on the external face to which I have a neighbor. Okay, this much we can do. Okay, and now we are looking at the set of nodes in V. These are all the nodes in P. That is all the nodes that belong to the internal face that have an incoming path to V. And our claim is that this in V can be encoded very efficiently because it is made up of at most two consecutive segments of nodes in P. Okay, so we claim that this is the picture. We can find two segments, and in this case, we can say all the nodes that have incoming paths to me are lie in the segment A, B, and C, D. And this means that even this node, all the nodes that lie in these segments that are in P, have an incoming path to V. Okay, so this would be, if this claim holds, it gives a very efficient, in just polylog and bits, it represents all its incoming neighbors from the internal face. Okay, so to prove that, I just need to exclude the option that maybe there is a third segment. Okay, so let's see why a third segment cannot exist. So assume that we actually have a third segment. That means that we have here a vertex Y that by the assumption, it has, because it is a green node, it has an outgoing path to at least one node, say V prime, on the external face, but not to V, because if it had an outgoing path to V, we wouldn't included it in the yellow region. Okay, and we have this X node that actually have an outgoing path to V. In one case, this path goes like that, and it intersects the red path of Y, and we get it, actually there is a path from Y to V, so we end with a contradiction. In the second case, maybe the path from X to V takes this kind of route, but then again, we have a node Y prime, which by assumption, it doesn't have a directed path to V, otherwise we would have included it in this yellow region, but it has some path, red path, to one of the nodes, but this red path must intersect the outgoing path from X to V, and we get a contradiction because actually there is a directed path from Y prime to V. Okay, so using these two claims, we get that indeed every node V on the face, okay, can compress its information using just polylog and bits. And by letting all nodes in the green nodes just broadcast their identity, it allows every node to decode what are the outgoing neighbors of V. So this is what we need to do for every pair of faces on which our extended separator nodes lie. And because we have at most log n many faces, we have at most log square n many pairs. So we end up with sending the polylog n bits of information throughout the entire network. Okay. So let me at this point just sum up. In this work, we provide new planar reachability algorithms for single source, for even multiple sources, if they all lie on the same face. One very intriguing open problem that actually was the reason, the main motivation for me studying these problems, concerned the single source shortest path problem. Currently, we have a D-square round solution from the work with Jason last year, but I'm very interested to know maybe one can provide a D-round algorithm. And because there is a relation between SSSP and reachability problems, I hope that that might be the first step towards providing such an algorithm. So thanks a lot and Shana Tova.